Good morning and welcome all of you. I am Dr. Mohamed Najar. My presentation is on the prospective utilization of geopolymerization on the consolidation and value addition of aluminium industry rejects. This slide presents the technical background of me. I am a chemist holding PhD in applied chemistry and affiliated with Jawaharlal Nehru Aluminium Research Development and Design Center, Nagpur, India. I have 23 years of association with JNRDDC as a scientist in various domains. My major research areas are industrial waste processing and product development, geopolymer, development of rapid analytical methods for in situ and ex situ applications, hydrometallurgy, and planar chromatography. I have good number of research publications, patents, book chapters, and conference presentation in the areas of waste management and geopolymers as well as building materials. My presentation briefly covers introduction, solid waste of aluminium industry, material properties, material input and waste generation related to primary and secondary aluminium production, source and characteristics, vision for sustainable development, geopolymer and advantages, product features and critical parameters, future scope and conclusion. Generation of rejects or byproducts is an inevitable part of industrial progress. Therefore, waste management is a matter of utmost importance in view of environmental concern and large accumulation of unused rejects. Mining, refining, and smelting are the major steps involved in the metallurgy of aluminium. Different types of byproducts are generated at every stages of the metal production and leading to the large accumulation of solid rejects having varying chemical and physical properties. Aluminium industry represents both primary and secondary aluminium production, and the overall upstream activities of metal production generates variety of solid rejects which are broadly classified into processed and unprocessed materials. In general, the rejects of aluminium industry origin are aluminosiliceous resources such as high silica and low alumina fractions. They are left unused and kept as future resources or partially used in landfills. Over the years, the outlook on process leftover or byproduct has been changed, and the leftover materials are considered as the best resource for secondary applications. Solid rejects of aluminium industry are precisely inorganic materials, and most of them are mineral-rich secondary resources. These materials are readily usable resource for industries such as building and construction, road construction, paint, pigment, and paper industries, ceramic and castables, and also useful for extracting valuable mineral values such as rare earth and precious metals. Both primary and secondary production of aluminium are left with variety of solid rejects which are useful material of productive applications. Many of the rejects from aluminium industry appears in the form of ready usable form. The advantage of rejects from aluminium industry is that they possess innate material synergy among themselves and many rejects materials of other sources such as steel, power, oil, biomass, etc. That means based on the chemical and mineralogical composition, these materials can be mixed together and make a composite of better quality for specific applications. The details are discussed here as alternative resource for the production of different type of building materials based on a non-fired and chemical process route. This presentation precisely highlights the potential of the processed and unprocessed solid rejects of aluminium industry origin as resources for making geopolymer products along with technical hints of value addition for commercial exploitation. The material input and quantum of byproduct generation is very typical for primary aluminium production. The raw material input for production of 1 kg metal start with approximately 4 kgs of bauxite and the bare process yield approximately 2 kgs of alumina. Further, the energy intensive electrolysis process additionally consumes approximately half kg materials in the form of carbon and cryolite. Since the quantum of waste generated represented the extent of pollution and material loss, there is a need for reliable and applied process options of rejects generated during the mining, processing, production as well as recycling stages. Secondary aluminum production or aluminum recycling also generate different type of waste materials. The major solid rejects generated during the aluminum recycling are filter dust, salt slag and furnace lining. The chemical combination of these materials are good enough to make suitable combination material with other industrial rejects or rejects from primary aluminum production. Let us have a look on the processed and unprocessed rejects of primary aluminum production. Low-grade bauxite, overburdened laterite, kaolinitic condylite, partially lateritized condylite, lithomargic clay known as saprolite are some of the major unprocessed resources largely associated and available at the bauxite mining site. Processed rejects of aluminum production mainly represent red mud, aluminum dross, and spent pot lining material known as SPL. These reject material have distinct characteristic features, chemical composition, and mineralogical composition that differentiate this material from the parent bauxite or the starting material used in the process. Kaolinitic condylite KK have similar properties of PLK and existing beneath the bauxite layer. KK possesses more silica, alumina and less iron in the chemical composition. In India, the bauxite mines at Eastern Ghat region located at Odisha and Andhra have PLK and KK horizon. Saprolite is composed of clay minerals that results from in-situ weathering of bedrock by acidic groundwater. A complete laterite bauxite profile usually comprises 4 horizons and rests on the parent rock which provides the source material for bauxitation. In most of the bauxite deposits of Western Ghat, Maharashtra, Chhattisgarh, Jharkhand, Gujarat rest on saprolite zone. Lateritic soils are formed in the tropics through weathering process that favor the formation of iron, aluminum, manganese and titanium oxides. This consists of minerals such as kaolinite, quartz, hematite, aluminogoethite, gibbsite, bohemite, diaspore, anatite, rutile, etc. The laterite contains high iron oxide, low alumina and high silica. The laterite derived at the bauxite mine is generally known as overburden laterite, which is removed from the top layer during the mining activities. Aluminium dross, bauxite residue known as red mud, spent pot lining or SPL, filter dust, salt slag and furnace lining are the major processed waste or reject material generated during the aluminium production. Red mud is the largest solid waste and least utilized one of all the solid rejects generated. Secondary aluminum production is mostly unorganized and have no comprehensive data about the reject generation and reuse and its utilization. Red mud is the largest and least utilized solid rejects of aluminum industry. 1 ton of aluminum metal production approximately generate 3 ton of red mud. The characteristic features of red mud is the high percentage of Fe2O3. Almost 50% of the total mass constitute the Fe2O3 along with good percentage of alumina and silica along with sodium and calcium. Other processed rejects of aluminum industry containing aluminosilicates are SPL, anode buds and aluminum dross. Of late, the industrial rejects are considered secondary resources for manifold applications involving recovery of mineral values, precursor for onward processing, as well as raw materials for product development. Resource augmentation based on workable utilization of reject presents the successful model, which highlights the use of minimum processing steps, low emission, energy efficiency, speed, low cost, and marketing options, etc. The vast increase in carbon dioxide and waste generation in recent decades has been a major obstacle to sustainable development and sustainability. In construction industry, the production of ordinary Portland cement is a major greenhouse gas emitter with almost 8% of total carbon dioxide production in the world. To address this, alkali activated materials and geopolymers have more recently been introduced as a green and sustainable alternate on ordinary Portland cement with significantly lowered environmental footprints. Their use to replace Portland cement products generally leads to vast energy savings and reduced use of virgin materials, resulting in a sustainable concrete production. By doing so, it reuses the solid waste generated in industrial and manufacturing sectors, which is aligned with circular economy. In turn, it reduces the need for ordinary Portland cement and its consumption and subsequent emission of carbon dioxide to the environment. As displayed in the previous slides, the chemical composition of almost all solid rejects of aluminum industry well suits for making geopolymer based cementitious material for building and construction needs. The possibilities need to be explored in commercial point of view towards sustainable production of aluminum metal in primary and secondary sectors for establishing the successful model. Aluminum industry rejects possess high mineral values and excellent properties suitable for making sustainable building materials that are useful for infrastructural and construction applications. Sustainable construction refers to the adoption of building design, construction methods, and materials that are environmentally amenable. Through sustainable construction, we optimize the use of natural resource by recycling and reuse of material so as to reduce our dependence on natural raw material. The rejects and discards of processed and unprocessed materials of aluminum industry are aluminosiliceous in nature. It contains good amount of alumina and silica in amorphous, hydrated, and combined form. The chemical nature of this material is well used for making geopolymer-based building materials as received or in combination with rejects from other industry origins such as steel industry, biomass, power industry, or mining rejects of non-ferrous metals such as manganese, zinc, lead, etc. Geopolymers are amorphous aluminosilicates which can be produced by the reaction between silica and aluminosilicates in alkaline medium at ambient or elevated temperature ranging from 25 to 100 degrees centigrade. The technology was first introduced by Joseph Davidovich in 1978, and his work shows that its adoption could reduce the carbon dioxide emission caused due to cement industries. Geopolymer production process is simple, energy efficient, and eco-friendly. It exhibits excellent durability and good mechanical properties and can replace conventional materials from low-tech to high-tech applications. In general, every material is suitable for geopolymer production which contain free silica and free alumina bearing mineral phases. The advantage of geopolymer is that geopolymerization process is one of the cost-effective and environment-friendly process route for converting different type of industrial rejects into useful materials, especially into building units. The geopolymer process or geopolymerization required no heating or firing. The process can take place at ambient temperature and no emission is taking place during the process of geopolymerization, and the binding is taking place without the use of cement. Synthesis or production of geopolymer involve three process steps: mixing, molding, and curing. JNARDDC conducted thorough studies on synergistic utilization of about 75 industry rejects in combination with aluminum industry rejects for making geopolymer products for building and construction. Lightweight, form type, sandwich type, and hard and high-strength products were developed by the non-fired route for suitable commercial exploitation. The studies identified good synergy among aluminum industry rejects, steel industry rejects, as well as biomass-based rejects such as rhesus ash, bagasse ash, and corncob ash, etc. for development of green building material based on geopolymerization. The three simple steps of mixing, molding, and curing makes the geopolymer matrix. Mixing for alkali activation of raw material is most crucial since all alkali activated materials are not make the geopolymer products. To make geopolymer matrix, low calcium aluminosilicates are generally preferred. The reject materials such as PLK, KK, laterite, etc. are best suits for making geopolymer matrix. The structural units of geopolymer is different from the one of alkali activated slag. Geopolymer have three-dimensional structures while the alkali activated matrix have no three-dimensional structure. They mostly exist in Q3 structure. So even if alkali activated materials have higher strength than geopolymer, they have very pure durability properties than geopolymer. Alkali activated materials are not polymers, so they cannot be called geopolymers, and many scientists and civil engineers are mistaken alkali activated material for geopolymerization. The combination of alkali activator and raw material forms the mixed design. Both alkali activator and raw materials could be single or multi-component mixture. The preferred alkali activator is sodium hydroxide in view of low cost and availability. For mixed alkali activator, sodium silicate is used with sodium hydroxide in specific molar ratio depend on the chemical composition of the raw material of choice. The raw material is also in use as single or multi-component mixture based on the concentration of silica and alumina in the individual material components. For example, if we use red mud as a raw material for making geopolymer, the availability of silica is bare minimum. To compensate this, a siliceous material like fly ash, KK or PLK could be added with a weight by weight ratio to compensate the availability of silica in red mud. In geopolymer matrix, the crushing strength is one of the important factors to use this material for building application. The strength of geopolymer products depends on the concentration of activator medium, material composition, and ratio of components in the mixed design. Therefore, the utilization of the geopolymer product has to be decided for making suitable alkali activator mix for dissolution of alumina and silica from the raw material. The crushing strength or compressive strength of some of the geopolymer matrix we have derived from aluminum industrial rejects in combination with other source material are shown here. Here we have achieved the crushing strength ranging from 10 to 25 MPa, where the minimum required crushing strength is 3.5 MPa for its use as building material. The use of mixed raw material facilitates the availability of alumina and silica for faster reaction in alkaline medium. For example, red mud is mixed with fly ash and rhesus ash, and the geopolymer matrix have shown about 19 megapascal of crushing strength. The input of fly ash is not suffice the easy availability of silica in view of the presence of quartz instead of amorphous silica. The requirement of amorphous silica for alkali activation reaction is achieved by the input of rhesus ash. Similarly, the required crushing strength for a specific combination matrix can be achieved by the selection of suitable material combination or by changing the ratio of material input, or we can change the concentration of sodium hydroxide and sodium silicate in the activator medium. So the flexibility of choosing the concentration of alkali activator and the mixed design as a whole makes this technique more preferable for making geopolymer matrix for building and construction application Or the same metrics can be used for making low strength material for low load bearing application such as decoration purpose, wall tiles or partition walls, etc. When we make geopolymer for construction and building applications, the following parameters are decisive and related to the material properties. Crushing or compressive strength of geopolymer is directly proportional to alkali activator concentration and curing temperature. Water absorption depends on the curing temperature and dry mix composition. That the physical synergy of material have a direct impact on water absorption. Increase in molarity and decrease in curing temperature, efflorescence of geopolymer increases. Density of geopolymer not depend on the concentration of activator. It mostly depends on the nature of raw material composition. Increasing building construction is one of the fastest growing drivers of carbon emissions. Therefore, energy conservation and carbon reduction in building have become increasingly crucial in the context of global carbon neutrality. Construction is the second largest industry in this world. Embodied energy, carbon emission, economy, utility, durability, and comfort are the main concerns of current classical building design. In order to reduce the carbon footprint of infrastructure, it is important to account the energy that is embodied in the materials that we use. Embodied energy is a sum of energy requirements associated directly or indirectly with the delivery of goods or services, including the energy used to extract, manufacture, and transport all the materials to be used. For the overall analysis of developed geopolymer, it is observed that with the increase in the sodium hydroxide molarity, the compressive strength, embodied energy, and carbon dioxide emission increases. A comparative study on the variation of embodied energy and carbon dioxide emission with respect to the increasing concentration of sodium hydroxide in alkali activator medium is shown here. The dry mix design used was a mixture of fly ash and laterite in 1:1 weight-weight ratio. It was observed that the XRD data or mineralogy of material is useful for choosing the right combination of raw materials based on the presence of active mineral phase within the component oxide. For example, the prominence of crystalline quartz and amorphous silica in total silica, as well as more active gibbsite, less active bohemite, and least active diaspore in minerals usually present in low-grade bauxite, overburden laterite, and other clay mineral rejects at different ratios in total alumina for alkali activation at ambient condition. This information of active mineralogical phases within the specific mineral oxide is also useful for measured use of alkali activator, that is a combination of sodium silicate and sodium hydroxide for geopolymerization. The reserved use of alkali activator in geopolymer facilitate better economics and quality of geopolymer product. Proper use of alkali for activation of active mineral phases in the raw material marks low efflorescence and material strength by encapsulating the less or non-active mineral phases or mineral components within the geopolymer three-dimensional structures based on the tetrahedron sharing of active alumina and silicon atoms. Further, the limited or controlled use of sodium hydroxide in the alkali activator keeps a cap on the emission of carbon dioxide as well as embodied energy in the overall geopolymer matrix. A comparative study is presented to affirm the superior quality of geopolymer based building material. Physical properties of overburden laterite based geopolymer brick was compared with the commercially available burnt clay and fly ash bricks. The comparison showed that the density of OBL brick is 12.5% and 12.2% lower compared to burnt clay and fly ash bricks respectively. The achieved compressive strength of OBL at ambient temperature is far more than that of burnt clay and fly ash bricks, which will ultimately help in saving energy required in case of heat curing. Overall, The developed geopolymer brick using laterite as primary raw material resulted in performance improvement. Wherever higher strength of brick is a criteria, these geopolymer bricks can be conveniently used for construction purpose. The following are the inferences of the case study. Compressive strength of OBL geopolymer brick is as high as 23 MPa. The water absorption and efflorescence are well within the permissible limit given by Indian standards. Compared to burnt clay and fly ash brick, the basic properties of geopolymer blocks developed shows that it can be used in building and construction as a substitute for burnt clay bricks or clay products, depending on the purpose and engineering models. Apart from that, the described process, geopolymerization, can contribute significantly to the environmental preservation, since there is a practical possibility of converting large quantity of aluminosiliceous industrial rejects as alternate building materials. This mineral-rich resource needs to be exploited with respect to the chemical and mineralogical parameters for developing value-added products at ambient conditions, thus saving energy, environment, and natural mineral resource for future needs. The scope and application of geopolymer are not just limited to building material. Toxic immobilization by geopolymerization, 3D printing related to building and construction, preparation of geopolymer ceramics are some of the latest attraction of geopolymerization. Coming to the conclusion, geopolymerization is useful for making wide range of building materials without firing and emission of greenhouse gases. Building and construction industry possess the space for consuming largest volume of industry rejects as geopolymerized building materials. Solid rejects of aluminum industry origin are best suited for making wide variety of building materials with or without the addition of materials from other sources. Chemical and mineralogical data of raw materials need to be considered for making mixed designs of geopolymer product for reduced use of commercial ingredients as alkali activator. Since the embodied energy and overall carbon dioxide emission is directly proportional to the alkali activator composition, calculated use of sodium hydroxide is advised for making activator composition. Scope and use of geopolymer as a reliable medium for containing heavy metal pollutants, radioactive elements, and other toxic components for safe disposal need to be investigated. बहुत बढ़िया है। Thank you all for the patient listening. My contact details are provided here for future correspondence.